Hello, my name is Jemael Nzihou. I will be presenting a different evaluation for predictive model in data science. So basically, we're exploring basic essential techniques to evaluate model performance in predictive analytics. We examine like metrics, visualization, and optimization like strategies for both regression and classification models. So the way we're proceeding with the analysis is through the iris flower data sets. And we basically load the data sets and then feature engineering. So how it's going to be conducted will be we selected the data from Scikit-learn data sets, which provides basically a starting point for our analysis, and then we move to the feature engineering. So we're gonna create like a new feature and combine the pedal and saddle dimension so that we can create a new variable, and then from there we're gonna like validate the data integrity through exploratory analysis. So in a nutshell, we're just trying to see if our combination of the new variable impacts the data basically. So how we're gonna be doing that? It's we're gonna do a train test split validation. So after obtaining the data, so we split basically through a 80-20 split ratio. So that's gonna stratify put that into like groups, which and then it's gonna enable us to randomly get some states of the data set fixed. And then after doing that split, we're gonna verify the method. The classification, the class distribution will be checked across, between the original data set, the training sets, and then the test using a value account function. So once that's done, we're gonna visually confirm if our models were actually effective, and then through the use of Seaborn histogram show how consistent the distribution was across the dataset partition. So why do we even care about stratification basically? Well, we have multiple reasons enumerated here. So first, for fair representation, to ensure that each class is proportionally presented in both the training and the testing sets, and to avoid biases, because if to prevent the model from favoring dominant class during the training, because if we have a dominant class, then we won't have a fair assessment of the analysis. So it has to be, that's why the bias has to be prevented. And then we have to look at the critical aspect for small data sets, especially in our case because we have just 150 samples, which is pretty small for the iris data set. Usually for bigger samples, we shouldn't have too much of issues, but since it's 150, then we have to consider other factors. And then also to improve the generalization. So because when we deal with the model learns patterns from all classes, just not the majority ones. So here the data set was sized up and then balanced. So as I mentioned earlier, we had 150 samples. So for the 80-20 split, so we ended up with 120 for the training set and then 30 samples for the testing sets. And each set was represented proportionally in all the sets basically, which ensured that our model learn and test against representative data. So here at the bottom we have basically the class distribution of the data sets. As you can see, we had the original data set, which is represented in blue. We have the training sets in green, as well as the testing sets in red. So on the left hand side, we have actually the class 0, and then in the middle we have the middle cluster, class 1, and then on the far right we have class 2. And then as you can see, everything seems to have the same height, which shows that okay, our model is actually effective, and then we have an equal distribution through the data sets. So the key factor that helped us gauge and then quantify the data was actually the matrix here, which was the mean error, the mean percentage, uh, the mean absolute percentage error, the mean absolute error, and then the mean square error. Basically, as you can see, the linear regression and the random forest. The random forest basically constantly outperform the linear regression across all the matrix basically. So it handles basically non-linear aspect of the data set and show robustness to the outliers. And then this is also the other factor that we took into consideration, where we had the accuracy, the precision, the recall, as you can see here. So that's why the random forest was actually more robust than the linear regression. As you can see here, the numbers actually uh, confirms our analysis. And as far as the key insights, the random forest is still superior. And in class 2 we had some challenging in the ensemble advantage. So we even further our analysis by looking at the residual plots, and we identify basically the error patterns in the regression models, as well as the random forest, which shows more uniform residual. And then we also use the confusion matrix on the right hand side at the bottom, which classify the result by class. And then the random forest basically achieve a perfect prediction for class 0 basically. And for the analysis of error, the error analysis, so we had a specific miscellaneous in class 1 and in class 2. So as you can see here on the residual plots, the linear regression is basically moving away from the 0 line. Basically that shows that it's not really a good model, because a good models basically stipulate that anything should be close to the 0 line. As you can see, the random forest residual, which is represented by the orange line, is close to the dotted line, so which actually confirms that our random forest residual is actually effective compared to the linear regression. And then for the confusion matrix, this was the result. So we have class 0 performance, which was actually perfectly predicted with accuracy and all sample correctly identified. In class 1 we had some issues. One sample was misclassified with 90% accuracy for this class. And then in class 2 we had to observe some challenges where two classes samples actually misclassified with 80% accuracy, and overall accuracy we have a 90% total accuracy. Most error occur in class 2 classification. And then here is basically a summary of the random forest classifier performance. As I mentioned, we had accuracy of 90%, the precision close to 90 as well, recall close to 90. So most of the the random forest classifier performance was close to 90 as well. So, and then as you can see, the details in the decision tree, we show that, okay, we had, more precision in all the elements that actually we wanted to target. So despite the fact that we had some error, but we can still improve our analysis, that's where the recommendation comes in handy. So we enhance like our feature engineering by creating a composite feature that better separate class 2 from others, which transform the existing feature using the polynomial of interaction terms. Furthermore, we had hyperparameters optimization, which implement like the GridSearchCV to find like the optimal parameter. In a nutshell, it focuses on like the tree depth and estimator counts for like the random forest. And later on, we actually advanced the assemble method, which explore the XGBoost and stacking classifier. You can think about it as like combining the model prediction for improved accuracy. And then we ended up with like the cross-validation strategy with the k-fold cross-validation with, grouping, with stratification, which ensure like, the robustness of the performance across different data subsets. And the final insights, as I mentioned, the random forest was actually the best model in this case because, it excelled in both regression as well as classification task. So the impact in business, so these models enables more reliable prediction for critical business decisions. You can use that in retail, healthcare, as well as, other businesses. As I mentioned, retail for demand forecasting, healthcare, automated diagnosis, and manufacturing like quality control to detect like the defect in, the quality of the product. And the next step, we implemented like the recommended improvement for even higher accuracy. So this concludes actually our presentation, and then this is the reference. And thank you very much for taking the time to watch the presentation. And if you have questions, you can email. Please reach out at zabatishu@gmail.com, or for more, documentation, you can check the GitHub at the link below. Thank you.